Okay. Hi, guys. Thank you for coming. My name is Mario Fusco, and here we have my colleague. Introduce yourself. No, no,
Francesco
not
Nigro.
shift. Okay. Francesco Nigro. We both work mostly on Quarkus this day, more mostly concerned about the performances of Quarkus, and we are both from Gorgonzola. If you don't know, it's like 15 kilometers east to Milano. So if you like cheese, please come visit us. Uh, okay, so who is into AI this day or LLM or is playing with the stuff? Okay, shame on you because you are helping killing the planet. You are wasting lots of energy. Well, not wasting, but using. The blockchain people was wasting it, but that's a different story. We are trying to do the opposite. We are trying to squeeze as much performances out of our CPU and try to help green computing by save some energy. So uh, our story is also as a, let's say, green background. Okay, what we want to do today is give you a very short introduction about benchmarking or what it is and why you should do it, and maybe how. And then we will have the central part of the workshop that will be about a few example of mistakes that we have made while doing benchmark, while using JMH. Mistake from which we learned something, and so we want to transmit what we learned with them and discuss them because they are interesting use cases. Okay, so in general, what is it benchmarking? Is measuring a process, okay, on one side, and try to find patterns and best practices, basically to save resources in the broader possible term. Resources means, okay, of course, in our case, CPU cycles, but also maybe shrinking the memory size. Uh, in essence, use our hardware in the best performing possible way. Okay, but and of course you when you do benchmarking, you evaluate a lot of metric, evaluate your performances, but I believe that these performances are often misused for a different reason. I mean, we use those figures not because to understand what that figures mean, which is the central part of benchmarking, but to, let's say, show off. So demonstrate in a way or another that you see my framework, my library, my tool is faster or more performing than yours. So this is what Francesco calls benchmarking. So you are doing benchmark, but with the only purpose of marketing your product, which is something that it's part of the game, but you should avoid if you are serious about benchmarking. And as I said, if you torture the data, you can basically extract whatever result you want. You can validate any hypothesis if you manipulate the data in a way or another, if you maybe change the benchmark to demonstrate your point. Yes, you will reach the result probably. You will demonstrate what you expected, but this is not really about serious benchmarking again. This is on the benchmarking side, which is something that we would like to avoid, as I said. Okay, so, okay, I already anticipate this stuff. We speak about benchmark in the computer, especially in the computer area, in the when we try to figure out how we can measure the resources used by our programs. Try to figure out if it is using the modern CPU in an effective way. For instance, and to do this, you need to go a little bit deeper also on the hardware side, also understanding what is happening on the hardware side. So this is because you want to use not only use the CPU, because you can have a very, very high usage in percentage, but you want to do useful work. If you are lots of branch misses, if you are a lot of cache misses, you are making your CPU to make lots of work, but it's not the kind of work that you may want to do. And this is something else that we want to measure, okay? And then the other aspect is that, of course, there are different kinds of benchmarking, and they mostly depend on the granularity of the amount of time that your benchmark takes to run. Okay, so if you are running, if you need to run a benchmark for a few seconds to figure out what's going on, mostly you are benchmarking an entire application or an integration end-to-end of different pieces, different components, different pieces of software, which is not something that we want to see today. It's not really the purpose of JMH. Normally you don't use JMH for this stuff. When you go into the milliseconds area, then you are maybe benchmarking a complete feature, but a single complete feature. You are not doing, for instance, that much I/O. You are not having processes communicating among them, and you are entering in the JMH area in this with this kind of benchmark. The real hotspot for JMH is the area even below, when you do micro and nanoseconds lasting benchmark. In this case, you are not even benchmarking a complete feature, but you are benchmarking a very small portion of your code. You are trying to isolate a problem first, and that problem, again, this is something that we said last year during the profiling workshop.
How many?
You
How many people?
Yeah,
was in the profiling workshop?
Okay.
Okay.
Just
And you
a
are still
few.
here. Well done.
Okay. You're brave. And this is something that we said during the workshop last year. You don't want to optimize your code in each and every part, okay? Because while doing it, probably you are, for instance, you are getting rid of a megamorphic call, so you need to refactor your code, but that code refactoring make your code less readable, less maintainable, a little bit more obscure. And this is not what you want in general. This is what you want in the hot path of your code. So it's likely in a section not bigger than the 3% of your code base. So the first job is to find which is the part of the code where your program spend the biggest part of time, and then you probably may want to do also some micro benchmarking in it in order to figure out how you can really squeeze the last nanoseconds out of that specific part. And yeah, I'm speaking about micro and nanosecond, and this is related also to once again to how our hardware also works. So you need to have a little knowledge of the typical latency number. This is a quite famous table on the figure on the right. You see basically exactly the same data, but just shown in a visual way. That's all, okay? And typically, what we will focus on today is the area on the top part of this table, when you have the lowest possible latency in the order of magnitude of a few microseconds, 3 microseconds in that case, no more. Okay, so this is the area when we will concentrate our investigations today. Okay, and yes, this is let's say almost 100% engineering and science, but from time to time, the result surprise ourselves, and we have our time and lots of fun actually, figuring out what's going on, what is happening, and sometimes the result is not even reproducible. So again, it is engineering, it is science, of course, but you learn a lot from experience as well. So when you really start doing this stuff, probably you feel lost because you missed the tool, you don't know how to proceed to investigate a result that you really don't expect. And in that case, again, you investigate the why that result come from. You don't change and torture the data to turn it into a result that you like. Okay, and okay, so we want to do benchmarking. We sort of understood why this is important. We want to save the planet. We want to make our machine as more efficient as possible. And so we decided to write our own benchmarking suite or benchmarking tool. And yeah, good luck if you do. Because you need to know at least what's going on inside the hotspot, what's going on inside the JVM, all the optimization that you can do. And this is more or less what you need to consider if you decide to write your own benchmarking suite. I don't remember this stuff by heart, of course. I believe that nobody does, probably with the only notable exception of Alexei. Uh, but yeah, it's something that you cannot make it right. Okay, there are too many variables to consider. There are too many optimization that can change the result in an unexpected way, and make your benchmark useless, not meaningful. And yes, this is a list made a few years ago, I believe, 2012.
Yeah.
12 years ago by John Rose, but I don't think that the things changed much in the latest year. So yes, if you want to write your own micro benchmark, then you have to read a few papers about micro benchmarking, understand how the warm-up phase work, understand a lot of all the work made by the hotspot, all the optimization and compilation effect made by hotspot as well to optimize your code. You have to consider simply too much stuff, and again, it's not something that you really want to do, I believe. Okay, so it's not that easy, and the reality is that it's very easy to get it wrong, right? So don't try to do this. That's my suggestion. And in reality, this happened to me in the very beginning of my exploration of this thing. I was working on my main project. I'm the project lead of Druze, which is the rule engine on Red Hat. I was trying to optimize some stuff and publish the result. And of course, the result was made by my benchmark, the benchmarking suite that I created myself. And the very first review that I got with this, okay, you are not using JMH. I'm not going even further reading your paper and analyzing your stuff. For sure, this result is wrong. Go back and try again. So don't waste your time. And yes, there are lots of stuff that can be incredibly wrong, meaning that the hotspots does things, right? And you don't know what it does. So with this very first self-made and ingenious benchmark, we wanted to check the time taken to access a field. Okay, we wanted to create a benchmark to measure how much Java take to do a field access, and we started this thing, and the JVM was skyrocketing toward incredible result. We had I don't know how many figures there are in this number, but an absurd amount of operation per second. The latency was 0 nanosecond. I mean, it was totally unrealistic. Okay, so we get this result, which is clearly totally garbage. Okay, we had the fastest CPU ever, but of course this is not true, and we try to figure out what it does, what is going on here, and if you want to go in deeper detail, of course, you can print the assembly, the equivalent assembly of this code. I'm not going to read this stuff. I don't do this very often, luckily. But in reality, this is a Java-ish version of what you see in what you saw in the former assembly. So the hotspot, the Java virtual machine, was rewriting that code in this way, meaning that in reality the access of the field was made only once and not 1 billion times as we expected in the benchmark, and that's why we saw these incredible figures. There's something to add about this, Francesco?
No, it was just,
Okay.
bad science
Yeah.
at the early beginning of the career.
Okay, so this is a very rookie, very initial mistake. I hope he will not do this, but this is just to let you know why you should use a serious tool to do this job. Okay, so okay, you got the message. Use JMH, use JMH. Even because if you start your investigation of a given piece of code or a given feature of the compiler of a given feature of your code, and then you write the benchmark, and then you take mistaken result, misguided result, and then you start writing a post about it, and then the bad practice spreads around the internet, and you have published a blog post about how fast and zero cost is the field access in Java, because you get that incredibly wrong result. And of course, you are doing a bad work not only for yourself but for the whole community, because you are publishing wrong result, misleading result, and you are suggesting other people probably to follow what you did when you got this wrong result. Okay?
And there is another part of this story that is actually a real story. Given how the brain of humans work, even if someone is going to say, okay, this benchmark was actually bullshit, I can tell bullshit. And the problem is that the brain separated the two information, is that result and bullshit. And just that result survive sometimes. So what exists in internet is persistent and is sticky. And then so lie is R. So you should be, very careful, because I didn't when I was younger. 5 years ago.
Okay, so I already discussed the main goal of GMH, which is creating this benchmark mostly in the area of the nano and microseconds. And the reason why it's called JMH is because it is an harness. It's a set of tool, a collection of tool that you can use to automate your benchmarking. Also, because typically you want to automate this in order to avoid regression, right? What you should do, or what we try to do, is also having this continuous integration stuff that not only check the test, but it's for performances. So from time to time, it runs also our JMH benchmarks and checks if we have regression in terms of performances. Okay, so you also want this tool to be automated in your continuous integration environment in order to figure out as soon as possible if you are doing well performance wise, or if you are introducing some unexpected inefficiency. Okay, so yes, this is the translation of that incredibly wrong benchmark in with JMH, using JMH. Okay, so this workshop is not about teaching you how to use JMH, even because the documentation is written very well, so you don't need it. As you can see, fully configurable with a few annotation. You write, okay, this is a benchmark, and you want to measure the throughput. You set a time unit. What is important is that you have a warm-up phase and a measurement phase. And the other important thing is that you have as many forks as possible, because with one single fork there are lots of stuff that could go wrong, in the sense that you could have an irrepeatable measurement, and you want to mitigate this effect with as many forks as
And
possible.
about the fork part, given that JMH take care of orchestrating through a runner, so a separate JVM if it's configured with more than one fork, to run the actual benchmark, that's enabled to have a clean separation between the two parts. So the part that collect the data, orchestrate starting the benchmark, and the part that is actually running the benchmark. And the more fork, the more JVM are going to be created in order to perform it, clearly, serially, not in parallel. So that's the meaning for fork.
Okay, and under the hood, JMH does this magic by generating lots of code. So the benchmark that you wrote actually is translated by a JMH in something like this, that helps you to avoid the typical pitfall that you can do because you don't know how the hotspots work, but JMH does. So it does is best to avoid this kind of mistakes. Okay, so for instance, this is something, again, this is not something that you have to write on your own. It's something that JMH generates for you. It's reading the time from the CPU is a costly operation, so JMH tries to do this thing as sparingly as possible. You see there which is the actual method under benchmark, but as you see, there is some boilerplate code, let's say, that JMH generates for you because it is the right thing to do when you are trying to measure the performances of a given piece of code. Okay, so again, this is not only not because I want you to go and check the code generated by JMH. You normally don't do this. Also because you don't need to do this, but just to uh, have a basic understanding of where the JMH magic is. Okay, so does this work now? Yes, we can have more meaningful result with this. Uh, but there are lots of things again that can go wrong. Uh, what's going wrong here? Where is the mistake here? Can you see it? Do you see the mistake? Maybe you know this joke. If you do, probably it's fine to find the mistake. Yes?
Yes, exactly. So
That's
the problem,
that's the point. The
no,
mistake is in the question. Often you are asking yourself the wrong question, and then you get the wrong result. You are not even the answer is wrong. What you are asking yourself is wrong.
exactly.
What you are trying to investigate is wrong. Go
And,
on.
and the whole point is that when you write a micro benchmark, clearly you would like to get some number out of it. So you eventually always get a number. It's like, LLM stuff. You answer, you get no, you get a question, and some answer come out. The problem in this case is that it's not just that what you should do. You would like to study, you would like to understand, to create a performance model of that piece of code, to better understand which part of it and how to make sense of the numbers that you can find. Because exactly like when we optimize code in order to get a specific average case better than others, we should remember that we have a runtime, the hotspot runtime, that try hard to understand what could be the best way to compile the code you wrote. And while doing it, it performs, as we said before, a lot of optimization. These optimization are probably the bad part, the enemy in the story of studying the performance figure of something, because they perturbate the model or the performance model of the application. And you would like to be aware, to study, understand, observe what's going on. And that's why having a test harness tool is important, because you just don't want the number. You want to understand what else, describe why the number it is what it is. And that's probably the other interesting part of this talk. It's not just a technical talk, so I'm not your therapist, but the thing is that when you do benchmarking, you actually have tons of bias to fight against. These are just few ones, so I try hard to make them into the context of benchmarking, but you can translate them in the way in which there was actually meaning when the bias has been described, and try to put it into the context of how you read benchmark. But for example, the confirmation bias, when you have a specific figure that you want to confirm, you start to ignore all the bad proof that will tell you that is not actually the thing. And you start to seek just that figure.
Yeah, and once again, you start torturing the data to obtain your
what you want.
confirmation. Yes.
Exactly. The anchoring bias, no, that could be translated in many different ways, but the anchor is, for example, what you know best. And then you would like to use that one to describe everything, because it's what you know best, so probably is the right tool. And it's one way to read these biases, so they are open for interpretation. The Dunning-Kruger effect, no, that's typical, because it actually applies to more skilled people and at the same time to average and newbie. Now, when I was younger at the university, for example, I finished the first 2 years in which, given that I'm a software engineer, I have done math more than my brain could sustain for the first 2 years. And at the third year, I was believing to be great in math. And I discovered, not even recently, that I was pretty bad. And the reality is that you don't know. You arrive at a certain point in which you believe to be good enough to understand things. And that makes you in a position in which you start to not observe the reality in an uncontaminated way. And that clearly is not good for science in general. So it's important to make hypotheses. It's not important to believe to them immediately, and not even believe that you will be able to understand whatever you will observe. You need to study to get better at it. The sampling bias, misinterpretation of data because the samples that are being collected are not meaningful, or they're skewed, or they are too much correlated between each other. That's another bias that can definitely happen. And the observer bias is another interesting bias. It could be interpreted, this one, said in different way, but one way that I love to think about it is while profiling. Now, you introduce an observer, and this is going to change the performance aspect of your application. You should be aware that these things exist. No, it's a bias not just for yourself. And you have a different way to fight against this bias. This is just a short list, and consider that the previous bias are coming from sociology, economics, psychology.
Mostly economics in the beginning. Yes.
They have a lot of bias,
Yes.
so definitely.
Yes.
But in terms of what we can do to get better, now, one that is not listed here is intellectual honesty. So to be honest with yourself. And that should be the very first one. But the other one are known as the three results. So the Occam results, the simplest explanation or methods with the least assumption should be preferred when interpreting benchmark results. It doesn't mean that it is the only one to seek, but the one that you can verify and negate to understand if it's wrong is clearly the first path that you should go. Not the one that will describe the world as the most complex machine that you can get, because it is way less easier to verify that it's wrong. Okay? And that this same thing is called even as a proportionality bias. You tend to have a very complex problem, so the solution should be incredibly complex. Sometimes it is not like that. The Itchen razor, what can be asserted without evidence can be dismissed without evidence. A benchmark doesn't have any explanation, motivation, anything to describe why the numbers are that way, can be safely ignored. Even you can stop reading immediately. It's bullshit. Hanlon razor, never attribute to malice that which can be explained by incompetence. That's another interesting one that could be read in different ways. For example, in the context of benchmarks, what I do on daily job, the people post me benchmark on their domain cases, sometimes with JMH, thanks God, sometimes not. And the thing is that when they run a benchmark, they don't really want to prove something sometimes. They are just trying to be trusty about what the framework does. They write a benchmark. It doesn't observe what is actually stressed during the benchmark, and they believe to be right. So they don't need to debug or write a test of that piece of code to make sure that it's hitting exactly what they want to measure. And they're not doing on purpose. They are not evil. But at the same time, on the other side, when you read the benchmark, you should be aware that that can happen to you and the other people. So be careful. And this is the quote in which the creator of exactly, JMH is complaining clearly that it's not nice to be presented on the slide, but is awesome, because this quote is what you get when you run JMH benchmark by the end. It's sticky, it's smart, it's been there exactly to put the bugs on your ear. You should always think about it. So the numbers below are just data. To gain a reusable insights, you need to follow up on why the numbers are the way they are. And that's it, really, because data is data. Information requires a process. You get just data out of benchmarks, not information. And that's why, in order to make sense of data, we will make use of another terminology that is coming from another great performance engineer called Brendan Gregg, that now works for Intel. He was working on Netflix. And he introduced the term of active benchmarking. That is exactly what JMH enables you to do. The fact that the JMH, or a good benchmarking harness tool, allows to attach something to observe what happened while the benchmark is running, it means that you just don't get the number by the hand. You You need to observe the whole process, collect counters, whatever that describe more about the dynamics of what's going on. And that's active benchmarking. It should be the only way in which you should perform benchmarking. And this is so important that, I got a friend of mine that was working for Hazelcast, that is Peter Ventier, and there was this nice tweet on Twitter, X,
post.
whatever.
Yeah.
Okay, that say that benchmark tools are often run without understanding what they are testing or checking that the results are valid. And the nice tweet of Peter Ventier said, never trust a benchmark run by someone who doesn't use active benchmarking. If you have an unknown bottleneck, your results will be completely unreliable. So active benchmarking helps to narrow down what's the resource, the most interesting resource that you care about and you are going to consume in your benchmark. So it's very important that you make use of it. And the other part is that depending we have the topology, the different type, the classification of benchmarks. And when you perform benchmark at milli, micro, and nano, and no, pico, no, thanks God, but nanosecond scale, clearly you should have some understanding of your hardware. You cannot ignore that it runs on your hardware. Okay, that's the other important thing. And as Mario said at the beginning, the JMH repository is incredibly good. Alexei Shipilev, that is the creator or one of the creator of the tool, is the creator, let's say. That's good, it's deserved. Being the creator of the tool, you spend a huge amount of time to do the right thing. So you have samples that are instructive. You can read. There is more to read than is not actual code, but it's good. It's what should be, because you read this and you can finish and you definitely get probably a better scientist at the end of it. And at the same time, you will feel that you have a lot to learn, but it's okay. That's what it is. So instead of using our samples that are, just to explore different surprising optimization that you can get, you should start with this. Okay. And now let's have some fun.
Enough speak.
Yeah.
Enough
spoke
speak.
A lot.
Yeah, with maybe too much. Yeah. My fault. Yes, enough speak. We can now try a few of our example. We are still keeping accumulating these weird beasts while we find them in this repository. So if you want to clone it and play it at home, maybe, or even contribute, it will be great. Okay, let's move to the
dead code elimination.
Yes.
So
This is the very first thing. Again, the very first and probably trivial mistake that you can make, but you can. And this is also to demonstrate that, yes, using JMH is a necessary condition, but is not sufficient. The other thing, of course, that you need to do is turn your brain on and figure out what's going wrong here. Okay, so what's yeah, I spoiled that something is going wrong, but let's see. Let's give this a run.
And the next time we will pick different names, because if you have a dead code elimination kind of test, you can expect what's going on. But
so let's also,
and for the people that are not used to JMH, the parametric part, it just run a full new trial of different iteration and warming up with that specific parameter on. In this case, is one of the key part of this thing. So let's say that we didn't attach anything about first, big disclaimer: we are running a micro benchmark at nanoscale from idea. There are performance engineers that can die because of that. Really, they can literally, I'm dying inside because of that. But,
Well,
as an
we
excuse.
triggered it, yes,
No,
from the IDE, but in reality, this is the terminal. So,
but still,
okay,
it could be too noisy. We measure first if it was noise enough and in which part. For the people that would like to try that at home, it would be perfect to use just a terminal. You can use task set to isolate the actual benchmark that is running. Ideally, you should install a TuneD because given that we work for Red Hat, everyone use Linux RHEL, no Fedora. You can install TuneD and use a specific latency profile that makes more reliable what you do, and you can fight against the Intel engineer in order to disable Turbo
okay.
Boost and what else it does in order to screw up the results. What we have done here is just to make it result as more stable as we could
Yeah, so this
for
is
the
the
bench.
bottom line. You should strive to have the less noisy and more stable environment that is possible. Ideally, you should have a dedicated machine. Maybe this is not often the case, at least for us, but if you launch the benchmark and then you get bored waiting for the result and start browsing the internet, well, probably
Don't
you are
spoil.
not doing.
Don't spoil.
Yeah. Okay. Can you read this, by the way, or should I make the font bigger? Upstairs, it's okay? Okay, I assume it is. So I just showing you the line of code that I'm launching. When you create a benchmark with JMH, it generates a jar with a main generated by JMH that you can launch, and then you pass as an argument the benchmark that you can run, and this is what I'm doing here. So let's start see what I'm doing here. I'm doing this computation in a loop. So I'm adding up a few number, 1000 in a case, 100,000 in the other. And let's see if the results are reasonable. Uh, the first thing that I notice here is that you see I get exactly the same result regardless if I'm doing this loop 1000 times or 100,000 times, which is a
Suspicious, I
little
would say.
bit suspicious already, right? So in reality, what's happening here? Okay, the name of the benchmark spoils the problem here. But what's happening basically is that this the method and the benchmark is returning void. So the Java virtual machine figures out, okay, this stuff really doesn't have any side effect, and you are not using the result that is returned by this method invocation. So why should I call it idle? And indeed, it's not calling it. Okay.
And playing with the different flags, because you can provide flags for your JMH runner about the JVM flags. If you turned off C2 compilation, that is one of the level of compilation, you can make still to do some work, for example, because the actual liveness analysis is not that sophisticated sometimes, and then you can still observe that things happen. The point is that, as we say, that the runtime JVM, and that's why you need the warming up phase if it's what you want to measure, clearly. It's important because you would like to get the most optimized code if you want that. And when you get there, you can have very surprising results. So this is a very synthetic and simple benchmark. But the reality is that even domain logic coming from expert on the domain that perform tests can have this problem. So you get a huge amount of operation happening in the benchmark method. You would say, okay, I'm fine. This is clearly cannot be that code eliminated. The problem is that maybe part of it will be. And that still means that the figure that you will get are not accurate. They won't represent anything. In this case, we have been very lucky because given that we had the loop number, at least we can think that maybe it's wrong, because it would expect that a different amount of iteration will produce some meaningful effect. And that's why you should make use of that information, because it helps you to create a combinatorial experiment in which you can better understand that something across the different type of tests should change. If it doesn't happen, you should dig to understand what's going on. You cannot ignore that part, okay?
Okay. So yes, and of course there's a trivial fix for this thing. In reality, it is enough to just use the result. I mean, if you return this result, then this result will be eaten by the GMH black hole that we will see what it is. But in a way, GMH make a use of this result in the generated classes, meaning that at this point the hotspot cannot do this dead code elimination again. And third and alternative way to achieve the same result is by doing this. Okay, this is quite a side effect of this compiler instruction. We are telling to the compiler, do not inline this stuff, and since we told this, it also doesn't perform any dead code elimination analysis. So this is a side effect, let's say, of this of the use of the annotation. I'm not suggesting to use this thing in this specific point. That I'm just showing you that by using it, you will have the side effect of also avoiding dead code elimination in this case.
If you show
We
the
can
color,
run, yes,
if you show the color, you will see that the results of this operation is not actually consume and return to the harness. So there is no return. It's actually executed. Check that not inline compute, it return void. So in theory, you would expect it to be that code eliminated. But given that this method becomes transparent, let's say, in terms of side effect, is going to be still performed. It is actually an implementation detail. And the fact that you know that, you will think that is less pure, the benchmark. It is not. It's rather the opposite. This optimization cannot be ignored. Or you should care enough considering the type of benchmark you perform. So if you are in the nano and micro, probably it matters. So, but be aware that it means that you will pay the full cost of actually calling a separate method. So the numbers won't be comparable to the other one. Or maybe, because if you do enough work, the actual invocation of the method can be negligible if compared to the actual work performed within the loop. So the last year we have been known as the guys that made the longest Hello World profiling workshop. So we started with the first one, it took like 2 hours. Close the door, please. The people can leave at this point. But there is a lot to say, even with a very simple benchmark.
Okay, I run again the benchmark with these 3 flavor, let's say, the one that suffer of the dead code elimination problem, and the other 2 that doesn't suffer of it because of these 2 different behavior. Here I'm returning the value, here I'm not, but the code that I'm calling is flagged with that not inline instruction. So this is the result of the dead code eliminated part, and of course it's a wrong and negligible number, and here you see the actual number. The other thing to notice is that this thing now is printing lots of results, not only the timing, and this is the first example that you see when Francesco spoke about the active benchmarking. We are not only reading the results of the benchmarking, but we are trying to figure out really what's going on in our benchmark, and printing some other stats that could help us with the understanding. So in particular, in this case, let me open. No. In particular, in this case, we told to GMH to also run with a profiler, which is perfnorm in this situation. Maybe you want to give some
Yes.
details
So,
about perfnorm.
how many people use Linux? Okay, it's fine. The problem with what else is not Linux is that sometimes other systems are not so observable. So clearly you shouldn't run benchmark on your laptop. But if you want to play with benchmarking on your laptop, with Linux you have different tools that helps to narrow down nano and micro and very tiny effect of what's going on both within the kernel and within your CPU and all the performance counter exposed by your CPU. If you have a Macintosh with Apple, you can do it with ASI Linux, but we have just two counters, probably, instruction and cycles. And the point is that when you perform active benchmarking on such tiny effects, you would like, something better that give more information. Among the different profilers that are implemented within JMH, perfnorm is using Linux perf, and it's normalizing the counters collected during the execution of the non-warm-up phase, normalizing them based on the number of invocation. So it means two things. First, your benchmark should have a steady state, because if you start to have benchmark methods that perform a variable length kind of work, the normalization that is based on an average will be completely screwed up. First thing. Second things, given that perf is attached as a profiler, assuming that the setup phase is very tiny and it starts after the warm-up, so when the code is no longer warming up, you should be careful, because if you attach the Linux perf non-profiler, but you have a too long setup, the data of the setup can leak if the duration of the setup exceeded the expected duration of the warm-up. So this is something to be careful about. In this specific scenario, we can formulate different hypotheses. So we expect that what we are performing here is a CPU work. If it's a CPU work, there should be executed some number of instruction, right? And the number of instructions sometimes is not definitely proportional to the number of iteration of the loop, because could be many ways in which the CPU can decide to make less instruction. But the point is that you should have some more. And what we can observe in this case is that the number of instruction here for the that code eliminated one is fairly low. And if you go on
it's
the other
impossibly low. I mean, it should
it's very low.
It should adding up 100,000 number, and it does this with 6 instructions. So
it's suspicious.
This rings a bell, right?
Yeah. And on the other side, if you look at the number of instructions for the non-dead code eliminated one, so Joe, just go a bit below.
Yes. So
this is this one, yes.
Yes. So you see the not that code eliminated bit. This time it's with 100 number, and you expect at least was only 1,000 number, and you expect at least 1,000 extraction to sum up 1,000 number, and indeed you have 1,300 instructions, right?
And related to this profiling tool, if you are curious about the meaning behind the counters, I mean, it's Linux. Everything is kind of reachable and documented. Sometimes the differences between different CPU architecture makes some counters, funny in the way in which they are produced, but the point is that it's all documented. This is not the case to look at the meaning of each of them, but if you have any question, I will try hard to not lie to myself and give a proper answer if you're curious about. So let's just move to the next one at this point.
Okay. So
black hole taxonomy, right?
So we will see a feature about the internals of JMH, which is called this black hole thing. So in essence,
Click.
yes, just to be clear,
Okay.
one second. What's the difference between uh, sorry, between doing this and doing this? Return it a value or a void is that in this second case the code generated by JMH can be consumed, okay, and the fact that JMH is consuming the result produced by this benchmark is also ensuring that you don't have any that code elimination, and the tool that JMH use to perform to consume the value is called black hole. Okay. Is this object that is again um,
Yeah.
GMH internal?
And if you
Okay.
click on black hole, there is, an explanation of what it does, and
Okay.
it
Yes.
it's interesting. Let's say, no, in many regards. If you want to pick in, a look in the internal, and it's definitely
Uh,
changed over time. If you want to do download sources, there
yes.
will be plenty, so it's nice.
So there's a few explanation on of how it works, of course. It, lots of tricks in it that again you don't want to do you on your own. There are some tricks,
Padding,
for
yeah,
instance, I guess here to avoid the false sharing
yeah,
problem, right?
I believe so.
Okay.
And still is not the funniest part of this one. So this is what the black hole should be. But one of let's run a black hole taxonomy, so I can show by the end of the benchmark probably the biggest mistake of when people do performance analysis. No, really, I'm not joking. It's not even a secret, but will be fun to see. So the numbers, the black hole loop, as the name suggests, is called in a loop of black hole consume. No? But the number are, I believe that Shipilev would expect that this number are especially high for a black hole loop compiler assist. And that exactly, and that's exactly what the people should do. Read the documentation. Come on, it's there. It's written. Just make it bigger, the terminal part, so we can read what's written here. Now, just go up, and there is something related black hole. Search for black hole or compiler.
Okay, these are the
Now, there is
flags.
an actual explanation somewhere. But in this case, there is not. So
Okay.
the point is that we added an option to not enable compiler assist black hole. If you don't do that, when JMH run, it will tells you that for this specific version of the JDK, the black hole implementation is based on a compiler assist version. That's why you shouldn't forget that it is a JMH harness tool for hotspot. Now, if you run it on J9, you can do it, but it wouldn't be that fun. Depends. And the thing is that if you disabled the compiler assist black hole, there is a software implementation that this test looks like a useless test, but this actually beaten us in production because given that in Red Hat we have a few frameworks that are CPU bound. We use JMH to track the change point detection of performance, the change over time. And there was a switch point in which we used the new JDK version, and we get the compiler assist black hole. And the absolute numbers are different. So these are the numbers for, so just go down and let's check the numbers that we got.
Yes, so just to be clear, this is the result that we are getting now with JDK 21, I guess we are running,
Yeah.
by using this flag. So avoiding using this black hole optimization. But this thing has been fixed, introduced with JDK 17. So
It's not
if
it's
you
a
run,
feature.
if you run a Java version before Java 17, you will have exactly this behavior regardless. So this thing has been fixed, and you can read
And
the.
let's show the numbers in case they are going to use the compiler assist. So if we go to the run2 sh
Okay.
script, we can just delete this one, the black hole auto detector. So go here and delete it or put it through, but you can just, it's the same.
Okay.
Run it
So
again.
look at this number. Sorry, we didn't mention this. So it is taking 300 nanosecond to perform this operation. And by the
That's a
way,
loop.
we didn't mention, I think, which kind of operation is doing. But the black hole also has a facility to consume a data. Okay, so I'm just consuming this data that is still up count.
And be aware that the fact that one is compiler assist and this one is software, instead even the optimization that can be performed on the loop maybe are the same, maybe are not. The point is that we make a loop just to magnify what are the effects. So a single black hole operation probably won't be that costly. But the point is that there is a performance difference. That's it. And when we were in production, we received a tons of alert that everything got super fast with JDK 21. And actually, not the problem, is that we moved to the new JDK version that was having compiler-assisted kind of black holes, and the number was completely different. Okay, that's why it's a real use case scenario, even if it's very simple. And
Okay,
run
so
it again.
remember this number. I will run this thing again.
No. Oh, yes, right. That's the other type of problem with benchmark. Maven clean package.
Okay, I don't need this. I
This
just
time,
changed the script this
yeah,
time, not the code. Yes.
exactly. And as you can see, it's around 2 order of magnitude. As said, there is a for loop. Maybe some optimization will be performed in the same way, but the point is that there is a difference, and you should make sense of it. So if you have someone in a PR that say, these are my numbers, and he's a nano benchmark, and he's on JDK 17, let's say, and then you have something on JDK 21, that's why JMH, when it started, he produced the output of the JDK version. That's important. Not just for the black hole. And there are even warnings about the black hole. And that's why first read the documentation, please. That's very important. Okay.
Okay. I think we can move to the next one.
CPUs.
The
Noisy
CPU scaling first. Yes. Okay.
Oh, yeah.
It's okay. Okay. So what we are doing here is using another feature of the JMH black hole. Notice that this time this is a static method of the black hole. So in this case, I was using an instance of the black hole, and in order to get this instance, you just add to your
Parameter.
benchmark method the black hole under in the signature as an argument, and if you do this, JMH will inject
An instance.
this black hole argument when it will run this benchmark. So this is the way to the very trivial way to obtain a black hole instance. In this case, I don't need this because I'm calling a static method this time of the black hole. This is a very useful method. We use it quite often. So this allows us to consume a given number, a fixed number of CPU cycles. Okay, so let's see what this work is. Okay, we have this parameter, so work is just 10 in this case, but of course you can, well, as you saw, there are lots of parameter in these benchmarks, and you can play with them at home if you want, changing this number or adding new parameters, so you can see the difference. But the point here is that, just to be clear, this thing is consuming 10 CPU cycle. That's
No,
all.
no, no, no. We wish. E-consume work
It
has been
consumes.
designed in order to have a linear cost as you add more work. But in terms of number of cycles, we don't know. It depends.
Mm,
So that's it. And we can check it with the profilers if we
okay.
want.
Right. And the other aspect is that you have this additional JMH annotation that allows you to say, okay, I want one single thread in this case, which is the default, to run this benchmark, or I want to run this benchmark in parallel, in this case, in 16 or in 100 different threads. Okay, so what we want to check with this benchmark is the effect of adding more thread up to a given number to check how well our CPU is scaling. Okay, so I believe is for the scale. No, this is the noisy environment, so we don't have the one for scaling.
We can change it. Yeah.
Okay. So clear.
And was CPU scaling. Yeah.
Okay. Sorry. Okay.
Okay.
Okay. So basically, we are running this benchmark that consumes a fixed number of CPU cycles. Um, and we are the only thing is that we are doing this in parallel with a different number of threads. So the first time we are using only one thread, and then we are using 16 of them, and then we are using 100. And uh, with this, our hope is to again have an idea of how well the CPU is scaling. So, by the way, what are your expectation here? I mean, every time I write a benchmark, before running it, I try to create myself a mental model of what I expect it should happen, which result I expect. Not to be, not to bias myself, not to have an anchoring effect, but to create a mental model. So the more the final result will be far from my expectation, the more I will be surprised, of course, but the more I have to investigate to figure out why I'm getting this number. So it's nice to create a mental model of what's happening here and what you should expect. So again, we are running this thing. I don't see. Okay, we are running this thing. Okay, this is in alphabetic order, so you see the one with one CPU first, and then the one with 100, one thread, 100 thread, and 16 thread. So this is what's happening. Okay. So let's try to first create a mental model and then check if this stuff is confirming our mental model. Uh, of course, when you run this thing with one only thread, you are not leveraging the multi-core capabilities of modern CPU. So you have a thread, one single thread that is doing its best and is actually doing its best for one thing that it runs serially. But then we increase the number of threads, so we increase the number of CPU that we, of course, in reality, that we are using. and we expect some sort of scaling of the throughput. So we expect to have to make more operation out of this thing. Okay, and this is one thing which is confirmed.
Yeah,
And
but still surprising because consume CPU 16. Now, if you can open LS top or LS CPU, you will see that this specific CPU, it's a 16 cores. Actually, there is a SMT that is the hyperthreading thing. So the actual physical core are just, and you can make it larger and press F, and we'll make it F. That's it. So these are the physical cores, but the actual number of execution unit looks like to be twice for each single physical core. It means that you can run two separate workload within the same physical core using the most of the resources. No, it depends. It's an architectural thing, and it depends by the type of instruction that are being executed. So the reason why we have a scaling kind of test is to observe if there is something that doesn't work with the base math, let's say. So we know that we have at least 8 physical core. So we can close this window because the number of physical core is still 8. And if we look at the numbers before that we obtain, the 16 case is not achieving 16, the amount of throughput, regardless. And there could be a lot of explanation for that, to be honest. So you can make a lot of interesting hypotheses about what could happen here. Sometimes the easier one are the one, like the Occam razor. Use the simplest explanation. What could be? The number of physical unit is not exactly right, but it's not the only one. It could be the governor, for example, because something that has happened in production, for example. So the people didn't tune the governor of the machine that was running a specific workload. And when that machine was running with too many threads or too much I/O or not enough threads, the scaling wasn't linear. Because even considering how the CPUs work for the turbo boost, they can decide to squeeze the most out a single CPU when it runs a single threaded workload. And for TDP reason, it decided to lower the value when there are too many. And this kind of stuff could be measured. So you can make use of perf, you can make use of other profiler to verify if this hypothesis describe what's going on. No. In this case, for example, we know, because I checked in the Intel optimization manual, that for this specific piece of code, you can achieve around 4 IPC. And 4 IPC is the number of instruction per cycle that you would achieve with this CPU with a single threaded workload running on a physical CPU that can run to hyper-threading thing. And given that we don't have more than 8 and is not a cache-bound kind of workload, we cannot achieve more than 8 when we have 16. Even worse, when you have 16, you can have more coordination. And when you have 100, is even worse, because clearly there is a cost in the operating system to interleave among all these different physical threads that would like to do something that is CPU bound on the CPU. And they have just a dedicated quantum of time to do it. I'm saying all this story because sometimes microbenchmarks are coming from CPU bound scenarios, so we are not performing any blocking or I/O related stuff with a huge amount of thread. And the people try to get some sense out of it. But the point is that if you exceed the available resources, you are observing a completely different performance scenario. So in this case, we put this benchmark so you can try it on with your CPU, maybe without tuning the governor. And I invite you to look at the performance data and check what's going on. And probably will be an interesting exercise to see why you couldn't get exactly 8, or how you could tune your operating system in order to get there, because you could actually. And running things from IDEA is not clearly great in this regard, because we add more noise in the environment. But still. Okay.
So, yeah, we can go to, let's say, a related example, which is um, with this example, we are still running more threads, but what we are measuring, it's the work done by only one thread. I didn't add any add thread annotation here, so it's running with one thread. But we want to, in a way, simulate that effect that I was mentioning before. Okay, you get bored while the benchmark is running, and then you start doing other stuff on the same PC, like browsing the internet, checking your
Mining.
social network. Yeah, okay, whatever you do, and you create in this way. You are creating a noisy environment. You are not allowing the hardware to dedicate 100% of its resources to the benchmark, and you can expect less reliable result, of course. So let's also give a run to this and try to make sense of the result again. Um, so it's 3. So yeah, to recap, what's happening here is that I'm benchmarking the same method as before, this time with only one thread, but the variability that we introduced here is that this thing that we are trying to benchmark may have a no noisy neighbor, or quite a few noisy neighbor, or a very noisy neighbors. I mean, 0, 4, or 32 threads that are performing the same thing. They are not under measurement, they are not going to be measured, but they keep the CPU busy doing other stuff instead of leaving the benchmarking method alone. Okay, so we can check again the result. Maybe you want to read them,
Yep.
Francesco.
And they're interesting because without noisy neighbor, we actually achieve this number that we still have to validate if it's such unnoised, but we will see in a few. With 4 noisy neighbor, that means 4 different process that are spawned by the benchmark and kept their own CPU busy, whatever has been assigned, you're still getting something similar. And if we cannot make sure, well, we can make some hypotheses. Effectively, we know that we have at least 8 different physical CPU. We know physical core. We know that that specific benchmarking methods at best is going to fully utilize a single core. So it means in total you have at least 5, and that saves at least other 3 spare cores that could be used. So in theory you have enough resource for this case in which the resource that is important is the CPU. Okay? And indeed the numbers look similar, but you have quite a bit more of errors. That could be anything, because we even touch the idea, so it could be even related to that, but we can look at it. And when you have 32 neighbors, noisy neighbors, clearly you go way beyond the capability of what that CPU can perform in terms of number of parallel tasks. And indeed you start to get a diminishing return, because for some reason something happened. So we can check in the actual terminal, because when we start this benchmark, we use active benchmarking. So we attach perf to see what happened. And you know that when, or you can look in the Linux programming interface kind of books, that what happened when you have an operating system that require to interleave different threads that should take care of using the same resources. Context switch happen. Context switch is one of the counters that are exposed by perf. So we would like to check if the number of context switch has increased as the number has been lowered here. And we can check in the actual output. So go a bit up because we have it. It's not print here, but it's print exactly.
Okay.
So if we check here, you will see go a bit up, and we will see the context switch. Thanks. So up, context switches. Okay, that's this number. Or actually, the absolute number is this. This is the rate. And given that we are not using perf norm, but perf, this is collected for the whole duration of the old iteration. It's not normalized on the methods. That kind of makes sense in this case, but let's go up and up again, because there was two fork. No, wait, here. 88. This is the case in which you have some noise in neighbor, but not that much. And as you can see, there is a huge difference in the counters, okay? And maybe you will speculate why the numbers are not in the magnitude I would expect. So let's say that you have a diminishing return in which you start to have 1/10 of the expected performance. You can measure that proportionally these other tasks are as noisy as using 4 times the amount of the whole CPU. You can do the math yourself and maybe find out that the proportion of context switch doesn't hold. And that's where the profiler comes in place. So when you get the profiler, you know the counters, and if you search for a switch task in the Linux kernel, you will find exactly where that counters has been changed. And you can check in which case it's going to happen. And you will find that maybe it's related to the CFS kind of Linux scheduler. So it means that depending how you configure that scheduler, you can get a different way to perform the switches or the number of in absolute of the switches. Okay? That's something that we won't do today, actually. So let's go up to the very first one, in which is the unnoised one, in which we have still 55. The other one was 80, probably, so it's a bit more, but not incredibly more. So, and the reason for that is because I've installed TuneD with the network latency profile that tends to be sticky. So it doesn't migrate and perform context switch if it doesn't have to. And that's helped a bit to reduce the number of context switch, even if increase the tail latencies. So that's the story about noisy environment.
Okay.
And in the real world, it could be, not just a browser while you perform benchmarking in front of an audience. It can be literally some scheduled task that run suddenly in your system. So having the chance to collect system-wide counters and evaluate in a different observed scenario what's going on with that counters is the way to better understand the reason, the motivation why the numbers looks what they are, okay?
And another thing that probably we didn't underline enough so far is that we focused, of course, on this number, but this other number is equally important.
Relevant, yeah.
And you see the clear effect here. I didn't mention before with the former benchmark run with the CPU scaling example, but you had exactly the same thing. The 100 thread and 16 thread runs had the comparable result, but the error amount was totally different. I mean, of course, the more you add a noisy environment, the more you have a CPU scaling problem, and the more you are creating an not repeatable run with lots of variation, and this will, of course, increase lots the error. So, for instance, give a look at this at the result of the third run with 32 noisy neighbor. Clearly this result is almost garbage to me. I mean, it's clearly not usable because the error it's more than the half than the result that I'm measuring. So the variability is so huge that easily I could do a second run and obtain a totally different result. And this is why it is important to also have a relatively high number of fork to reduce the amount of this error. Of course, during this workshop, we are using a super low number, which is not realistic. You should never run this stuff with only two forks. Probably 10 is a more appropriate number just to mitigate this effect of this error scaling and noisy environment possibility. Okay. Do you have
We
something
can
to
or
add?
make a small pause
Yes,
because the
yes.
hardest part come later.
Yes. So the funniest part. Okay, was really
Depends.
the introduction of our fun, but there will be more interesting example
Maybe lining.
with the three last. So I believe we can have. What time is it? Okay, we can have less than 20 minutes break. I believe we can start at 11:15 if it's okay for you. So in less than 20 minutes. Thank you. Please be on time. Thank you.
Vai Mario.
Okay. So let's start. Let's restart this. We have a few other example that we want to discuss. Let me close the other actually. Okay.
And thanks to have not run away in the meantime. That's good. Great.
No, even because now it starts the real funny part. So, what we want to demonstrate with this thing.
So we talk about optimization, right? So optimization perturb the performance model of what you would like to observe, but still can be a part of what you can observe in the real life. So let's say you have an application. This application it's using a specific profiler. This profiler tell us a story about megamorphic call. How many people knows about this term? Do you have any idea what it is? It doesn't count, Alexei. But yes.
Yeah.
Okay, the idea is that when you perform invoke interface bytecode or other code that can have different concrete type that are going to be executing that specific bytecode, the just-in-time can perform different profiling to understand what are the distribution of the types that are performing that specific call. And in different scenario, this can make the actual call to be performed in a very fast way, in which actually the just-in-time produce a guard against an if, literally, against a very specific type and go straight calling that method. Or in another case, it could even decide to put two guard for the two must observe, they only observe types. And if we go beyond two, it can decide to give up and perform the so-called virtual call. Even virtual call are definitely optimized by the just-in-time, but they are different. And the point is that in all these three cases, the performance of calling methods can have a different performance model, exactly because the just-in-time perform different type of optimization around it. So in this scenario, we are trying to narrow down this kind of behavior in order to make it reproducible and to study what's going on. No, I was thinking we were doing the inlining one first.
This
We can do
no.
it
Well,
later on.
we will do it later. Yes,
Okay.
it's the next one.
So let's go through the actual source code in this
Yes.
case. So the type profile pollution, the name is not by accident. If you search in the OpenJDK glossary, the type profiling is something, so there is an explanation, and the pollution problem is actually a proper name. So when you have, let's say that you are making use of array list, no, in one part of the code, a linked list in another part.
Which
If you have
something you
used
should
linked
know.
list here, you are doomed. No, I'm
Okay.
just joking. It's
Don't do
not
it.
right. It's just a tool. But the point, if you have more than one types, or 3 or 4, and this type form different call, and you have something that is using the list interface, for example, that piece of code, in different cases, it could be compiled in a way that its type profile, so the number of receiver, the concrete type observed could be different. And that the fact that it's not just one is called pollution, okay? So in this case, what we have done is to create 4 different predicates. So we have static methods, and we are saving this in 4 different predicate
Variable.
instance.
Yes.
Then in a static method is a very raw way to verify it. So please be gentle with us. What we have done here is to verify it by extracting get class. No, go in the static, Mario. Up here. We are verifying that there are actually 4 different class type. That's important. I mean, it's not important. It's just a safe net. In theory, it shouldn't be optimized away and they could become the same type, in theory. But given that it's part of what we would like to prove here, we cannot ignore the fact that in order to work this benchmark, these should be 4 different types, at least. Then we have other mechanisms to verify it in the meantime. But this is one easier way to do it. And in the setup phase, go a bit down. What we have an enum that describes the typomorphism. So how many types are being observed in the actual call, that we will look at it pretty much immediately. And we have a predicates array in which we are populating different types of predicates in it. In the monomorphic one, we fill the whole array of predicates with the predicate 0. So
It's
in the
always the
array,
same.
there will be always a single type.
So it's a monomorphic call. The compiler always see the every time it sees the same
single
call,
type.
so a single type, the same. The invoke interface is actually invoking also always the same concrete method. That at some point the hotspot has a chance to figure out that he can optimize this thing, probably do some inlining, and it does indeed.
Okay, here in the B case, we are populating, even and odds indexes of predicates with one type and the other, so 0 and 1. And in the megamorphic one, we are using 4.
Okay.
No? And it could be even 3, to be honest, but has been made 4 for convenience, because in this case, we have created a single array of predicates that always have the same amount
Size.
of the same
So
size.
that is not the factor. The factor, the only difference of these different runs is the amount of call site that the invoking method sees.
So here I'm doing something that will probably screw up Linux perf, because in the pollute at warmup, that is a parameter that can be false or true, we perform, let's say that our test perform stress two different type of scenario. That's just the motivation behind the benchmark itself. Let's try first with the pollute at warmup false. So for now, let's ignore this.
Okay.
And
yes.
just let's look. Go down.
And the other argument parameter that we have in this benchmark is that we do this call but this call either doesn't do any work at all, or it performs some work, and I will show you why we are doing this. Okay.
And
In
let's go
reality,
down now 1 second, Mario, because
yes.
we didn't show yet the benchmark
Okay.
method.
True.
So the benchmark method is asking for how much could be executed on consume CPU before performing the actual test. It's iterating among all the predicates, so it means that based on which predicates are being based on which predicates are being populated within the array, you can have different ones. And it's using a nasty trick coming from the previous part of our presentation. So we have this test with that is using the predicate in the actual array and the person that has been collected at the beginning. If you go down in the compiler controlled until line, just a bit go down, you will see what it does. So it basically asks predicates to perform a test against the person received. The important part, I mean, is not important, is a safe net in this case. It could be not important. We have decided to not inline the test with the method. This is because of my ignorance or a part of the internal of the JDK. So if we perform not inlining of this one, the compilation of the method test with will have very likely, if there are no changes in the type profile, a single blob. So it will be a single giant piece of assembly or big enough. And the types that are being observed for predicates will pile up based on what is being called here. There are few other cases like not invoke interface, because predicate is an interface. You can have even virtual call not based on interface but with concrete classes, in which there are further optimization performed at just in time, in which the type profile, so the receiver for a specific methods, could be even simplified and can become monomorphic again. Given that I'm not sure about it, that's a safe net. So in this case, I may be perturbating a bit the results because I'm introducing the cost to perform test with, but at the same time, I'm making sure that here it should observe different types. But given that these are just words, we will attach a profiler to find it out. And there are even other mechanisms like providing an output or the actual type profile for each receiver that is actually possible with enabling diagnostic on the JVM, so it should be possible. In this case, we are going to use a profiler for that. So the expectation here is that based on being mono, B, or megamorphic, we would expect to kind of change the numbers, the cost here. And if you look at the predicates instead that are 0, go a bit down, 0, in the source code. No, these are the predicates. So in terms of what they do, they basically do the same thing, the same amount of work. There is nothing really special, let's say, about it. No, should be resolved as compare. So it's stupid.
Okay, so again, the only difference is how many different method implementation the invoke interface is. Okay, so let's read the result, okay, and try to make sense of them. So with this first set of benchmarks, when I'm not doing any other job other than doing the invocation, you will see that there is some relatively small difference between the monomorphic and the bimorphic case, but then you see a dramatic performance decrease with the megamorphic case. It's not almost. It's more than the double than the bimorphic one as time consumed. Okay, and the reason why we added the second run, also doing some additional job, is let's say twofold. The first of all, it's not to scare you too much about this problem, and second, because we wanted a more let's say realistic use cases. So normally you do this call, which can be mono, bi, or megamorphic,
Together.
but you also do some other work, right? So the difference is a little bit more hidden, a little bit more buried among the other job that you hopefully do. Okay, so this should be, let's say, the case when you don't do any other job is just to stress the problem as much as possible and make it as evident as possible. The second, when you do some job, when we added some job, is the more, let's say, real world use case. Okay, you actually do some job, hopefully, or rather other than doing the call. And you can see that in this case, the difference between mono and bimorphic is it's upset in practice. You still see a difference, of course, with the megamorphic case, but in percentage, the difference is much lower. Is of course mitigated by the amount of the other job that you do.
And that means that the reason why we got that far in this benchmark, in order to provide the kind of controlled, and to be honest, is not even as much controlled that it could be. Because I'm performing a loop, you can get a loop unrolling, you can get a lot of different quicks that are not completely under your control, or they could be, but your amount of work in order to get to the perfect benchmark, whatever it means, could be infinite, believe me. The point is that at a certain point you decide for the so-called optimal stop. So, and be able to control enough a specific part of your benchmark in which you don't know yet how much is relevant. It's good to find if it's relevant, and then you can add other part, like the consume CPU part, that emulate other work in order to find out if it's really relevant, relatively other stuff that you can do. And that is just the step before trying production. Because the production it becomes the actual final outcome of these efforts, in theory. Unless you are doing for academic purpose, and you can dig as much as you want, for the rest of your life about benchmark, basically.
Okay, I'm running the second.
No, we need to show first the sim profiler output for the first one.
Right. Okay. Okay.
So
okay.
how many people knows a sim profiler first?
Let's take this thing aside
Okay.
for a
A
bit.
sim profiler is a profiler that can produce flame graph. How many people knows about flame graph? Way better, so it will be easier. Now, in this case, that's more complex. How many people are colorblind? Okay, I hope that still will be visible for the right part, because we are making use of colors in order to outline specific optimization of the just-in-time. So I will try to describe and use the laser to show the relevant part. In the meantime, Mario is opening up. If you didn't use the sim profiler yet and you have the chance, it's a very convenient profiler. So you can find it for free in GitHub and just grab it and try it. It's very nice. So which use case is this? So for most of the people knows about profilers. So these are the profiling data. Yeah.
This is the case for the monomorphic call with no additional job made. You see here that
the colors, that the part, the green
maybe you
one.
Want to explain? Yes.
The green is not inlined one. Who knows about inlining? Okay, that's important first. Inlining is one of the optimization that could be performed by a just-in-time, in which the actual call to perform a specific work is not happening, but the actual body or whatever is basically copying in the caller methods, making the call to disappear. It just doesn't exist, period. So, and inlining is de-optimization with capital letters. So, inlining widen the scope of the optimization of a compiler. And not only for nano benchmark can make a lot of difference calling through a methods that does nothing against calling nothing, because the actual call will make a lot of difference. A sim profiler provides a way to walk the stack in Java in which it can provide a visual outcome in the flame graph to show what's being lined and what's not being lined. In this case, the test with the method is the one in which I suggest through the compiler control of JMH to not inline it. And the fact that it is green, it means it works. So basically, it's not being inline. Test with. And test predicates on the other side is the loop. And the loop is being inlined, so that's good.
Okay, let's see the megamorphic case.
Mega. And that's interesting. So there is a nice feature in a sim profiler 3.0 that allows to put on what are so-called synthetic frame introduced by the JVM, the actual concrete type that are being observed for megamorphic call. In this case, given that it is an interface, invoke interface call, the name of this stub is itable stub in red, if you can't read it. And you will find here that there are 1, 2, 3, 4 different concrete type that have been called in the invoke interface. So what our hypothesis is that our benchmark was actually able to perform predicate.test having 4 different receivers. That is the very first test that we perform on the static part, in which we make sure that we are talking about 4 different concrete types. And indeed, there are 4 different concrete types. So we can observe it here. And the fact that it has a width, it means it costs in terms of CPU cycles. And even if, to be honest, I don't remember by heart if a sim profiler decide the width of this based on the frequency, the relative frequency of appearance of the receiver.
Yeah.
But in this case, it's just active benchmarking in the sense that we attach profiler to observe if the actual expected dynamics of the system kind of match it. You can do basically the same, that would be even better, by collecting logs. Because these kind of logs, the inlining, compilation, decision, type profiler are all available on the JVM. So it's still possible. But this one is pretty convenient for this kind of test, to be honest. And something that it's a bit unexpected, and I think it's kind of wrong, is that these are in Aqua. Aqua should be inlined. I think that it's a problem of a sim profiler in this. Because on the right side,
I believe, yeah,
you
these
can
are
check
the actual
yes. Call. And in theory, with the megamorphic call, it shouldn't be inlined. That's the whole point, let's say. So for this benchmark, very specific benchmark, when the type profile or the predicate test is polluted by too many profiles, it becomes megamorphic, and a very simple call became costly because it's not inlined. That could be, the actual observation.
So-
but we can go deeper to go in that.
So in reality, what is not in line is the actual invocation of the lambda, as you can see, and then internally to each and every lambda, then you can, when you invoke a lambda, you have these 2 steps invocation. You are invoking this stub generated by the compiler, and then you invoking the actual implementation of the lambda. So in this case, what you can see is that this stub cannot be lined because this is the megamorphic part. And then inside each and every of these, you can inline the single actual implementation that it does. So you have a skidding effect. I don't know if we want to mention.
Now, this one, I don't know if it's going on, to be honest. So let's check another part of this story. So
Okay.
we complain, not complain, we are trying to evaluate if in our methodology these things really matter. And we actually have a case in which we have a job 20. So if you replace 0 with 20 for the megamorphic one, we can check what happened if we have a consumed CPU near the invoke interface. Now, the actual virtual supposedly call. And that's what happened. So maybe in production, that what you got is that you have a tons of other things going on, typically logger invocation with the formatter. And near to it, you have your well-studied invoke interface with the megamorphic call. So the relative cost makes negligible the fact that it's megamorphic. It's not always completely true, but the reality is that in this specific case, it is. So having a controlled environment in which you can decide how much is important, which part, if they are doing what you expect they are doing and you verify it, it's good enough to decide to not go deeper in that rabbit hole. And that's it. No?
Okay, and yes, just to be clear, now the biggest part of the work done during the execution of this benchmark is what we call the side job of this megamorphic invocation. So this is the actual job, and then the problematic megamorphic invocation is a little bit, the effect of it is a little bit hidden on this part. But of course, the problem is still there. It's just that it is smaller in percentage. It is a smaller fraction of the whole benchmarking execution. Sorry.
No.
Nope. Okay.
We can try the second one or go
Yeah,
straight to the
I ran
inlining,
it
Mario.
already. I ran it already
Oh,
with this
nice.
polluta to warm up.
So
You may want to
explain
explain
what it does. Yes, this one is using the polluted warm-up part instead of being false to be true. But what it does, the polluted warm-up, and this is literally running with scissors. So not definitely what you really want to do. But given that it's interesting in this
it's
regard, we can look at it what it is. So polluted warm-up, it try to perform test predicates here in the setup phase. It's really bad because a compiler can perform compilation in an asynchronous way. And the fact that you don't know when it kicks, for example. But still, in this case, we are trusted that we have executed the test predicates enough time, and it actually is performing not in line the work, so it won't be that code eliminated, in theory, enough that it's going to pollute the profile way before the warm-up is starting. And later on, we perform a different decision. So we let the just-in-time to believe that the actual profile is made of equal probability for 4 different types, 2 different types, 1 different types, but we end up using a single type in the actual benchmark. That looks interesting because sometimes, and this is coming from a real-world use case,
Yes.
given that I'm the performance lead for Quarkus, sometimes I have to look in very bad benchmarks. And a very well-known benchmark is called Tech Empower. Tech Empower perform a warm-up phase in which it performs very weird decision in what kind of operation it should perform. They just in time truly believe about this bad decision. And then when it runs the actual benchmark, the profile of few parts that prove to be hot, important, are completely polluted and not optimized. And because of that, I have to come up with this bad trick. There are definitely many other ways. And if you are curious about it, there is a very nice article from Alexei called The Black Magic of Dispatch, probably. And you can search on it. It's awesome. And it explains this and with even more detail if you are curious.
So in essence, what is it? The benchmark itself is not seeing, it's never seeing polluted invocation. It's always seeing a monomorphic invocation when the benchmark runs. The problematic thing is the setup. Before reaching the benchmark, we are polluting the call site with multiple different kinds of invocation. And then the benchmark is always run with the same invocation. The benchmark is always megamorphic. But at this point, as you can see from the result, it doesn't matter anymore. The hotspot learned that it is a megamorphic call, so it is not even trying to optimize it. Even if the benchmark is running a monomorphic invocation, it is treated as a megamorphic one. That's the problem, and that's what you see with this result.
And the reason why it exists is because the previous benchmark could be too biased around how CPUs don't, I mean, it was expecting branch misses to not be a thing. Because when you have the B and megamorphic one, we have an array by which we loop over it, and we pick a type that could be different. The actual chosen path to decide which actual call has to be performed is nothing different from an if. It's a comparison. It has to pick which direction of call should be performed. And when you have a branch, you can have branch misses or not, depending if the CPU is good to predict it. And in this case, I'm providing this example exactly for that reason, because this example at runtime is always picking the same type. So that if is perfectly predictable. And if you want to test it, you can attach perf norm and check at the branch misses. But we have another example for this.
Yes. Let's move to the other example. So we mentioned in inlining. So we thought it was nice to have a more proper example to show how much important inlining is. Probably inlining is the optimization that the hotspot does. If you are losing inlining, you are losing a very relevant fraction of the optimization that you can have in your code. Okay. Before I explain what this thing does, notice that I configured this JVM parameter that extracts the JVM. It gives an upper bound of how many inlined method it can have in a stack. Okay, so
at which level?
Yes, it can have at most four inlined method in a row, and then it doesn't inline anymore, and then it can start relining again. The default for the JVM of this value, I guess, is 15, right? So by default, this value is 15. I'm setting it to 4 just for the sake of this benchmark to show in a more clean way what's going on. But in reality, you can have exactly the same problem just with a different depth of the stack. Okay. So with this premise, let's see what this thing does. What I'm doing is that I'm filling this string with what is size. I'm filling this string with 100 uppercase A. Okay, and then I have a test, which is the method that is actually under benchmark. This one is the test to check if this char sequence is null uppercase. So since I'm passing to it 100 uppercase A, it will check all the 100 character, and it will return true. This is what happens here.
Small disclaimer: this is coming from real world again, because there is a project called Netty that mess up a lot with HTTP and different, higher level protocols.
Yes.
And in this case, HTTP2, for example, should check if everything is lowercase or uppercase based on the HTTP headers. So they have different benchmarks that have been provided by random people on the internet to say, oh, the way in which you check the lowercase or higher case is wrong, that's the right way. And that provides just a number with benchmark like this. And the reason why we have to dig into that is, oh, come on, I didn't observe anything wrong in the actual production number. Let's check what's going on here. And that is still a valuable
And
lesson, no?
and yes, and then the other variability is the depth in the stack where I call this method. So 0 to 5 means that I call with 0 I call that method as the first thing, and I'm done. And otherwise I add one more method on the stack if the depth is 1, and otherwise I go to with 2, 3, and 4, and 5. I mean, you have understood. It's just how deep is this in our stack is this invocation. That's all. Let's give a run to this thing. Um, and let's try to figure out what happens. Any guess? I mean, what do you believe it will be the worst run of this 6 possibility? Which one will be the worst one? Any guess?
At which level? 6.
Sorry? 6. You mean, okay, the 6th, the one with 5. Okay, let's see what happens in reality.
Let's make it bigger.
Yeah, 1 second.
Yeah. And remember, the benchmark methods are two. One in which we have the compiled until line, and the other one in which we just let it loose.
Okay, so yeah, actually we are running this thing twice. One, it's because we want to control exactly which one is the method that is not in line. So the counter start from there, here, and there we don't have this control, but it's mostly it's just the same thing. It's just one call depth. So let's give a look at the result of this controlled use case because it's the one more understandable and trackable. Okay, so see here, this is quite surprising, isn't it? I mean, with all the depth level of invocation from 0 to 3, you have the same result. And even with 5, you have practically same result, comparable result.
Slightly
But
worse.
see what happens here. What's happening here? Let's discover this with the flame graph. Okay, so this is, okay, we have a surprising result. We don't know what's going on. We want to know. So let's give a look at the flame graph and check if we can figure this out.
And
So
consider that this one is already in a controlled way, so we kind of know what's going on. But in the actual published benchmark that we received in the repository of this project called Netty, it was actually a benchmark that proved that the version A against the version B of a different algorithm to perform the check of the lowercase or uppercase was incredibly faster in one case and incredibly bad in the other one. And the problem is not the benchmark. In fact, it's fine. You can share on repository. But if it's just the number, that's the problem. Because the number just show that A is better than B. You need to observe what's going on.
So this is still in the happy path. Everything above the method under benchmarking is still in line because I didn't reach the limit. Okay, this is the fourth invocation, so it starts from 0, 1, 2, 3, 4, and this is in line. Okay, And then let's see what happens when we add one more.
The four,
Okay,
yeah.
no, let's see what happens when we add two more, which is still
Interesting.
the good
Okay.
part. Okay,
This one, it's again a sim profiler in this specific scenario doesn't show the
it's
right
lying.
code.
Yes.
Yes, because in theory, what should have reported is that the mid one till check uppercase, so from
From 1 to 5.
1 to 5 should be aligned. This one, no. And this one is going to be aligned
So
again.
by
So
default, the problem is that by default, a sync profiler shows as
the top,
correctly shows as inline only the top method in the stack, not the one in the middle. Okay, there's a way I will show you to also check to also make this call in the proper color in the aqua color since they are inlined, but the bottom line is that this method is inlined, which is the one that interests us. Why is it the one that interests us? Because the other one are just single call, but this charret is executed in a loop of 100 times. So this charret is called 100 times. So let's see what happens in the non-happy path, in the situation when our benchmark performed much worse. Just to be clear, in this situation, right? You see, it's 10 times slower, 10 times. And the problem is clear now. The problem is that all the two methods in the for loop are not in line, because at that point we exactly reached the limit that we imposed to the virtual machine with that flag or for consecutive inlining code. We are in the unfortunate case where the method that is called many more times is the one that is not inlined. And this is dramatically affecting our performances.
exactly. And the reality, make sure, is not because of the call. We don't know yet. We know that if you have a wider kind of, perspective to the compiler can do a better job. But when you have not inline methods, it became transparent what it does in this case, the char at is reading is, in theory, should perform bound check, if you look at the code, read if it is a string, for example. But in this case, it's even simpler. It's a byte array read. Very simple. It should be a trivial kind of operation. But that kind of operation required, because how the Java runtime, the Java spec work, you should raise an exception because of bound check. So bound check should be performed. And usually you can hoist up some of the check before the loop is actually starting. But you cannot anymore if you have the inlining that is not performed. So in this case, we are not speculating too much why are that bad. But we know that inlining is playing a role in this story. And that's the, good enough to describe what we need. No?
Any question on this? I mean, again, this look at this number. Really, this is just made ad hoc to demonstrate how important inlining is.
And controlled it. So in this case, if you go in the is upper, so not the controlled
Yes,
one.
it's same thing, just one level different. This is happening at
Exactly.
level 3 instead of 4, just because I'm not saying at this point you have the inlined, so the inline counter starts 1 minute before. That this is what happens.
Exactly. So when you have benchmarks that are CPU bound and you represent, I mean, the algorithm presented doesn't look like to be that dramatically better. An easy check is the inlining things. It's so easy. You can just print inlining, or just you can attach a profiler and you will immediately know if it's playing some role. And when you get better into it, that it means that you have suffer a lot for many years, probably you will directly choose to not inline and have control when you are performing this kind of stuff, if it matter. Okay, so we have another
Yeah, we have
example.
another similar example on the same topic. The difference here is that I'm doing a recursive inlining. So I don't have a method A that calls B, calls C, and calls D, but I have a recursive invocation, a method that calls itself. And I'm not using any JVM arguments here. This is because for recursing inlining, the JVM is much more strict. The limit is just one. So you have one invocation, then the second, and then it's not inlined anymore. When and so yeah, again, you can play with this parameter if you want, but what I'm doing here is that I'm doing exactly the same. I'm test using exactly the same method as before, but in this case, I'm using a recursive call with a counter. So this time is recursively calling this method 12 times. Again, this is a parameter that you can play with, and finally performing the invocation. Let's give this a run.
I don't know if we have it.
Nope.
We have it
Yeah,
in our scripts.
Okay,
We have it.
and the other little difference. Okay, this run. The other little difference that I have in this run is that, as I told you, by default, async profiler is not showing the inlining that happens in the middle of the stack, but you can fix this problem since sync profiler 3.0 with this command. Okay, if you add
Should
this
work.
command to async profiler when it's run, that then it will do something. I don't know what. Maybe Francesco,
Yeah.
you can explain to actually show the proper relining. So maybe you can give some more info while I look for
Yeah.
the proper
So
flame graph of this.
in this case, a SIM profiler is not making use of the usual way to collect the stack in in the JVM, but it walk the stack by using some internal structure. And that enable a SIM profiler to have information about inlining and provide this information when it's walking the stack to construct the actual samples. So that should be the theory. The reality is that it doesn't work.
Ah,
It could be.
it's broken.
It could be broken. So
Why? It
I don't
worked on
know.
my machine.
It is what it is. We have a refresh of the laptop. That's the beauty of
Ah,
real time.
okay. Sorry. This okay,
You can remove the C stack VM.
but you don't see
Yeah,
the.
yeah. In this case, you can trust or not trust my word and try by yourself. But what I can tell you is that usually
Okay,
the
shame.
fact that you have different heuristic or ergonomics for inlining based on being recursive or not could be pretty surprising to people. And when you have different algorithms, and sometimes algorithms are made recursive because they look more elegant, if they are performing very little work in that part, maybe it could be important to not making recursive, let's say, because of this fact. Or maybe it could be important, so it depends on your case, as usual. Let's see if we get any better.
Yeah. So
Okay.
in this machine, that flag is not working. I don't know why. But what you should see is that you should alternatively see one.
Aqua and green.
Yes,
Yeah.
a green and aqua method, a green and aqua method, a green and aqua method. Okay. This is should be the effect, and now instead you are only see the inlined one at the very top.
Yeah. And
Okay,
you can
sorry.
still observe something related to this by looking at the fact that is up 1 and is up 2 here, they, I mean, they have the same width, like there is no cost in transitioning
Because this is in
among
line
them.
and this is not.
And
yes.
that's why. So you can detect that there is a call,
Okay.
but the fact that he is in line doesn't make
Yes.
it costly, and he's not blamed, actually.
Yes, you can indirectly see which is the costly call and which is the one that has practically zero cost, because it's in practice it's not a call at all. The method has been inlined.
And still, the final performance, given that the check uppercase is similar, is the same code of the previous example. No, it performed the same amount of work. And the char at is being correctly in line. If you check in the absolute number, even if you don't have good inlining, but you have a chain or at least 6 different not inline methods, it's still it's not that bad, the performance. It was like 64 against 5 something. So maybe it's not that important. Maybe it is. Depends when you are lucky or not. So which level you are.
So the other relevant bit here is that as you saw, the Java virtual machine gives you a little bit of control of this thing on the current inline level using this directive. Don't start spreading this stuff around this code, please. I mean, I'm just telling you this thing exists. I'm also telling you don't use it. Don't use it unless you know very well what you are doing, and even if you are, don't use it. Because you know it's really tricky, and it's enough to change your code with one single more or less method invocation to completely destroy the effect of this optimization. So it's also a little bit brittle. We used it only to have a controlled way to fix where the inline counter start counting in this example.
And we can go to another real world, sadly, use case, the branch prediction one. Let's see if we have enough time. I hope so.
Yeah,
this is tough.
Okay.
So basically, this is coming from this other story, still related netty, because I spend a lot of time in that networking library. And basically, HTTP2 required to verify that a specific header is a pseudo header or not. The reality is that in a specific code path is always expected to be a pseudo header, and a pseudo header are already specified, and that they should be lower cases. So in theory, we never expect a check if something is a pseudo header to be false. It should always be true. And I got few mates in my companies that come at me with some real profiling data, and they say, okay, we have observed, and this is another performance team, so they are fairly good. They provide me performance counters and say, we have some weird behaviors going on in the validation of the pseudo header that is blamed too much. So it appears in real world data for a router made in Java, an HTTP2 router. So I made up this experiment to better understand what was going on. So I observed the real profiling data. I come up with finding the actual counters and which part was relevant, and I made a synthetic version of it in order to study what's going on and play easily instead of having an end-to-end kind of test. Clearly, this is going to magnify incredibly the problem. And sometimes it is what it is. But you need to make sure that it is still relevant for your original problem. And in this case, you can solve the problem to check if something is a pseudo-header in, let's say, 3 ways. One way it's by using an immutable set, for example. In another one, you can make use of a hash set. And in another one, again, you can use a switch. And I'm making use of this fancy new switch. And if you ask yourself, What is this next method? That's the funny part. So let's go in the next part.
Okay.
So if you click on next, so what I've done this time is to create an array long enough. Let's understand better what it is long enough. But in this case, trust me, it's long enough that contains different pseudo headers. These pseudo headers can be populated in two completely separate ways. In one case, it's using exactly the same literal string that is being used in the collections and in the switch, while in the other case is created by a new string that has the same exact content. No? And that, if you know a bit how hash map work, you should use equals, but the very first things that used to check a key is by having the reference equality. So having the same reference and having a different one with similar content is actually performing different calls. So it's important to go down both routes, depending what happens in the real production code. And what it does, this amount of different headers are being picked in some random order that is still reproducible because we use the same seed for random to populate this array of different indexes. And we tend to pick each time a different pseudo header. If you ask yourself why you do that, the reality is that it's what happens in the real world. So in our case, it's completely not predictable, the kind of pseudo header that you can receive, because the actual real world usage here is a router. A router can have tons of connection of different applications that does very different things. So it's not safe to assume that the order by which you receive the different pseudo header to be verified doesn't matter. So in this case, I played safe and I say, okay, maybe it matters. Because based on the way in which we are going to solve the problem to check against the pseudo header, this is going maybe to be relevant. And in the maybe lens is where we will use the profilers to understand if something is really relevant or not. No? So let's go and take a look at what we got. In this case, we have been even too much verbose. So open up the terminal. We have a lot of counters. So let's try to isolate just the three numbers that we care about. So we have performed the test by not using the same literal. Why? I made it for fun, actually, because I didn't know exactly the production code. When I talk with the domain expert, so the people that has worked on the router, they told me, no, we always create a new string every time. Not good. But still, that's why same is false. So I'm not using that part. The hash set use case.
Well, also the shuffle. I mean, this is really the real world use case scenario. When you have different instances of string, you always you don't have the same instance, and the things comes in a random order. In a random the protocols are used in a random way. This is really the real world scenario.
And in this case, we are in 21 nanoseconds per operation. That is, I don't know, if you remember the latency that each programmer should know, whatever, it's in a good ballpark. I mean, it's way more than an L1 miss.
Cache miss,
way
yes.
more. It's more look like L2, but maybe something else. So let's look what could be. And let's go down to see the other numbers. So hash set, immutable set with the shuffle through is getting 28. And what was the previous one?
21. Okay,
so this one is slightly worse, let's say. And if you go to the string switch, it's 31.
It's so a little bit worse.
It's definitely even worse. We have performed other tests because we didn't ask ourselves if shuffling, not shuffling, make any difference. So if you open the results.txt that I saved in the folder, so we didn't have to run it. Okay, we can check without the performance counters what's going on. And that's another interesting part. So I added the perf instrumentation. In this specific case, if you don't add the perf instrumentation, the numbers are very different. So in this scenario, there was a kind of observer effect. And that's why I'm showing this one here too. So it's not always that you have to run with the profiler and think it doesn't matter. Because as I told you, it's one of the bias, the observer bias. So make sure that it's not disturbing too much the behavior. In this case, the hash set is performing with, let's say, you can remove the same true because it's noisy from, reading the results. Same true can be removed, so it be less.
True,
Same
so
true.
this one.
These two. Let's make it shorter because it's easier to read.
Okay, so this one, for instance.
Yeah, and the one below, all the same true.
Okay.
Okay, that became much easier to read. Okay, shuffle. What changed? In the hash set scenario, shuffle is making some difference. And here is not making any difference. No, it is making still some difference. And here is still making some difference and you get even more. It's
a big
super
difference.
weird.
Yes.
So let me try to check if we have another run of the same benchmark, because these numbers doesn't look what I remember, to be honest.
Do you want to run it again? Or
There is another script, or is the last one?
no, this is the last one, but there is this result with the ISM.
No, go to the actual script. We can run it again, once again. So going and run 6 and remove the shuffle through, and you can add false comma. And let's...
You want to remove this?
Yes, and remove a sim profiler, because we are adding 2 profilers here.
Okay.
And let's run it again, this stuff, to see what happened.
Okay.
Because I do remember something, and I would like it to show up. So let's see if it's a real thing. So don't move anything, just let's wait and see what happened. Let me anticipate what could be. No, because it is not trivial. How many people knows how string hash code, what it is? Is a spec you can expect to change over time or not?
The hash code of a string.
Yeah, hash code of a string. It shouldn't change over time. The number, no,
It's
fairly
stable, yes.
stable. Hash map, hash set, immutable set, all they create a kind of array in which they can manage collision against keys. And when there are collision because of the size of the array and the hash code of the actual key, the collision required to be resolved. And based on the type of implementation of the hash map, there are different ways to resolve it. One way is to go through a chain of other key to check against equals, because they all have the same, hash code. Or on the other side, it could be just by moving to the next slot of the implementation. So it depends what kind of hash map implementation is. And the point is that when you have, let's see if the numbers hold, but the point is that when you have a collision, a decision should be made. That it's a branch. And given that you can receive it in very weird order, the different headers, sometimes you can have collision, sometimes not. And that introduces a branch. And if you feed with enough random inputs, the keys, you can get in the case in which the collision matter. And if that matter, you get a branch miss. And a branch miss could be very costly in relative term on CPUs. So let's see if we are actually getting this scenario or not. So the hash set was getting
I believe you want to see. Okay, this is not doing shuffling. Maybe the one with shuffle through is more relevant, right?
to be honest, I was expecting to have the same number. So it means that my actual assumption was wrong. Let's check the branch misses.
The branch misses. Ecco qua. So
In the false way
in
and
the false
in the
way
true
and
one,
the true, it's much bigger, of course.
it's way more. Okay, that tells a different story from my expectation. So I suffer from the so-called confirmation bias, because when I run this benchmark in a different scenario, I got the collision detection against a hash set to be actually be performed based on the sequence of the keys. And because of that, I trust that was always like that, was stable enough to be performed today in this benchmark. But given that we are lucky enough that we perform active benchmarking, and I know that I fed with enough different and random input data my benchmark, I can see that actually there are more branch misses when you have shuffle through. And that means that I'm probably getting a problem of suffering of that collision detection again. And the thing is that I don't know yet till I actually print the assembly and go even deeper to look when the actual branch miss is going to happen.
And yeah.
Okay. And let's go even down, because we have the other results that are still interesting.
This
in
is
which
with the immutable set.
the immutable set is 27 nanoseconds per operation.
With the shuffling.
Yeah, with the shuffling.
So it's still slower than the hash set implementation.
Even
and,
if we don't know yet why. So let's look at the
yeah,
branch
we don't know yet
misses.
why. Yes. And so ring switch with the shuffling.
It's really bad.
Sorry.
So
It's a little bit. It's a little bit worse.
And we can check the number of branches performed by the string switch, because how many people has ever looked at what it looks like, a string switch? First in the bytecode at least. Okay, so if we look at the bytecode of string switch, it actually pre-compute based on the literal hash code, a kind of binary search to find the actual key. So if you have very different hash code, you have each case with each hash code, and then a check against the actual key. And that's it. So you have several different branches. And based in the order of appearance and how much the CPU can be unable to predict what's the next one, you can get a certain number of branch misses. And the point is that the fact that the shuffle makes a difference is the important story. So right now is not a fight against which of this one is faster, but the curiosity is that it matters. That's the important part. And it does. And the fact that it matters in the real life, that's another part of it. So we study from an academic perspective the number of branches. We check if we have more branch misses. And we should ask ourselves, okay, I create this experiment, not very reproducible, my fault. But at the same time, what's reproducible is that the analysis of the counters that are being extracted still hold. So you get different performance because you have branch misses. If you are asking yourself where the problem is, you should go down the route of the actual assembly and check for that specific performance figure. And that can be even more fun and even more painful. It depends how you like to spend your time. And if you look at the t-shirt, it's fairly easy to explain how I spend my time.
Do you want to go through this quickly, or?
Oh, I don't know.
Just just to explain, maybe I believe that it's interesting the difference between the immutable set and the hash set, because people believe they
Right.
have that's
They are
not
the same. They
they are
think.
the
Yeah.
same, and they are not. Okay,
Oh,
so
nothing that couldn't be explained
probably
by
you
looking at
can
the source code.
find the data here while I'm
Yeah.
telling you. Uh, well,
Let me check here.
yeah, Francesco will show you precisely what's going on. But our finding is that okay, this thing surprised us a bit. We were expected a similar, very similar result, if not better, with the immutable set. The problem is that the main difference between the hash set and the immutable set is that the hash set is made in a way that the entries are always a power of 2. Okay, so when the hash set has to enlarge, it goes, for instance, from 32 to 64, let's say. The mutable set, since is mutable, it doesn't need to be enlarged. They also dropped this requirement of have a number of entry that is equal to 2. They have a number of entry that is in proportion with the number of entry that you put in the immutable set. For instance, if you have 6 entries, as in our case, they may want to decide that 10 buckets is enough, and it will be 10 forever. The problem with the number 10 is that it's not a power of 2. Okay, the consequence of this is that when you are looking for the right bucket for an hash set, you can use some bit shift operation to find the right bucket. While if the number of bucket is not a power of 2, then you cannot use anymore this bit shift trick, but you have to use a modulo operation, modulo the number of the buckets. And the modulo operation, of course, is much more costly than the bit shift one. And there it lies the difference between the immutable set and the hash set implementation. I don't know if
Yeah.
you. Okay.
I just found out the relevant part. 2 points important. In this profiling data that I collected, I didn't add enough resolution for the cycles counters. So, and one of the good things of using JMH is that it will complain about it. So if the numbers of events are suspiciously low, it will complain for good reason. In this case, given that I knew the distribution of it, I could just speculate that was good enough for my case. But clearly, if you see a warning like that, you shouldn't ignore it. That's very important. So in this case, one of the beauty of the JVM, no, if you look at the immutable collection set and something, is going to perform a modulus operation against the actual capacity of the array to find to find the actual position within the array. And when it does it, the beauty of the just-in-time is that it can transform what are supposed to be an IDIV assembly operation, because when you have to compute the modulus, you need the reminder. The reminder of operations still require to make use of division in theory. In practice, the just-in-time is incredibly smart. So in few cases, you can decide to transform this operation in a different way. And in this case, it's making this optimization of using IMUL with some magic numbers. So if you search on GCC for these numbers, you will find that other compilers, when they are aware, and the just-in-time can be aware at runtime, of specific operation in a specific ballpark of numbers, they can perform this kind of optimization to speed it up, the operation. But the reality, if you don't have to do it, you go faster. So in the case of the hash set, for example, it doesn't perform anything like that, because one of the optimization made by hash set, or hash map, even better, is to have the power of 2 capacity, as Mario has said. And in that case, computing the modulus is just a shift. And it's not even required that just-in-time will do it. It's actually in the Java source code. So in this specific scenario in which the hash set was populated in a specific way with a specific load factor, and the immutable set was in exactly specific way, the numbers we collected represent kind of realistic figure in which the branch misses are important, let's say. At the same time, the way by which we perform that additional operation of finding the right bucket in the hash set was important enough to outline a difference in performance between immutable set and hash set. But still, be very aware of the ballpark of the numbers we collected. The numbers we collected are in the nanoseconds length. So we are talking about something very small. And that means that you should really be aware if that's your problem in production before going that deeper. Okay?
And before making your code less maintainable and readable in the name of the performances, again, in my opinion, this deserve to be made in no more than the 3% of your code. So strive to have the remaining 97% as readable and understandable and maintainable as possible, because the bottleneck, if the bottleneck is not there, you are polluting your code for no actual advantage, for no actual reason. Okay, so I guess we can use these last 2 minutes to draw some
recap.
Recap, some conclusion. As you see, benchmarking is well, we have fun doing it, I must admit, or at least I
certain
do.
degree.
Yeah, a certain degree. I hope the example was interesting. The main, to me, the main bottom line is that the hotspot is smart a lot, and often if you try to outsmart the hotspot, the result is not that good. I mean, there are many amazing engineers working on it. It does amazing thing, and trying to convince the hotspot to do something different, it's often not the good thing. Benchmarking is doing experiment in a controlled way, so that's why it's as Francesco said, it's more similar to natural science, natural observation instead of a formal science. So probably
that's a sheep
you want to
one.
say want to say this about
this is a very nice quote from a much
Alexei,
longer
yes.
not of this workshop. This workshop is long enough, let's say, but was a longer kind of talk always made by Alexei, which actually the software engineering is a thing. It's in some regard is a form of science. We have proof, but the software performance engineering is slightly different in some regard. It's definitely even more science if you think about the science in the physics term, and it's more a natural one. So there is the empirical evidence, the kind of tool, the cognitive part that are something that you can get by having ODN on rotating a tree. That actually interview for Google probably. But and that's very important to have this distinction and be able to move across the two different worlds in a pragmatic way is the right way to address this problem. So sometimes you don't need to go that far. But if you have to, do it in the right way. That's it.
Okay.
So we have a huge amount of reference, but the last one is very important because yesterday there's been a very awesome talk on JMH. And I really think that, in a world in which we have too many AI-related talk, if we have in 2 days a JMH talk, that's great. I mean, it's not a repetition. It's a complementary kind of material.
We really believe that the two talks complement each other. René showed a lot more, simple in the sense, understandable, more common example. We try to went a little bit more down the rabbit hole by going through the assembly part, but
making it wrong.
Making it wrong in some case. So I believe they complement each other. They treat the same argument, the same topic at two different levels. So probably you may also want to give a look to Rene presentation if you haven't done yet this yesterday.
Yeah.
Okay, and that's all we have. Thank you.
All systems are nominal. Initialize Genesis